The third type of phase that we typically deal with in this course is the gas phase. In contrast to liquids and solids, which we assume to be incompressible, for gases, we typically make the assumption of compressibility. So gases, we say, are compressible. And all that means is that in these gas systems, we're assuming that the pressure is going to be a function of volume. Or, in other words, the pressure is sensitive to the volume of the system. And also vice versa. We could say the volume of the system will be affected by the pressure of the system. Okay? And so, to relate pressure to volume, equations of state are typically used. All right? And so you've probably heard the term equations of state in MEB 1. And all these equations of state do is they relate, or they give you some sort of mathematical tool for relating pressure and volume. But not only those things, but you could also relate pressure and volume to the number of moles in the system and also the temperature of the system. Okay? And so anytime you hear about equations of state, all that means is that it's some sort of mathematical formula that relates pressure to volume to moles and also to temperature. All right? But why can we do this? Why are we able to relate these four disparate variables to one another using an equation of state? Okay? Okay, and so I'm going to try and, show you why we could relate these four variables to one another by at least painting a physical picture for you. All right? And so I want you to consider this sort of physical situation. All right? So let's consider that we have, some sort of system inside a rigid container. All right? So the container walls are going to be rigid. They're not going to be flexible at all. They're going to be hard and durable. Okay? Now within this system, let's say we have some gas molecules. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So we have some gas molecules in our system. And we'll also say the temperature of the system, it's going to be room temperature. So we'll just say it's 298 Kelvin. Right? The system, the container, has some volume, which I'll call V1. And consequently, the system will also have some pressure, P1. Okay? And so those are the basic variables that describe this system. Now, the number of moles in the system, N, that's sort of easy to consider because that's just going to describe the number of molecules we have in our system. We have 10 gas molecules that I drew here. The volume of the system is also kind of easy to understand, right? That's just how big the system is. But what about the pressure? What is the P1 describing here? What does it mean to have P1 pressure? All right? And so at this point, what I want you to do, I want you to pause the video here, and I want you to think about what exactly does pressure describe about our system. Okay, let's continue. All right, so what does pressure actually mean? And so the way I like to think about pressure, so P, is that pressure describes the energy of gas molecule collisions within some volume. Okay? Alright, and so why am I describing pressure in that way? Well, let's go back to the physical situation that I drew here. Alright? And so the gas molecules we have inside our rigid container, they're not static, right? They're not staying in place. These gas molecules are going to be constantly moving around. And so I'm going to draw the velocity vectors of these various gas molecules here. Right? So they're constantly moving, they're floating around all over the place. Okay? And so because these gas molecules are constantly moving around, occasionally they bump into each other, or more likely these gas molecules will will collide with the sides of the container. Okay? And so these gas molecules are constantly moving around, they're constantly hitting each other, and they have some sort of energy, right? And so the pressure in the system is describing, how much these gas molecules are moving around within the volume of the system. And this sort of makes sense, right? Because if you even just look at the units of pressure, right? Typically we say describe pressure in pascals, but if we break down a pascal, all a pascal is a joule per meter cubed, right? Where joule is a unit of energy and meter cubed is volume, right? And so with pressure, what it's describing is the energy of gas molecule collisions within some unit volume, okay? And the temperature, T, this is going to control just the energy and force of the gas molecule collisions. And so temperature just controls the energy, while pressure is the energy divided by the volume. Okay? And so to illustrate this concept even further, what I want to do now is let's imagine that we take our system here, right? We take the same number of gas molecules, but now we're going to shrink the container down to a smaller volume. Okay? Right? So we have the same number of gas molecules, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? These gas molecules are still moving around all over the place. Okay? We're going to keep the temperature of the system constant. We're still going to say it's 298 K. But now the volume of the system, V2, is smaller than V1. Okay? And so in this case, we kept the number of molecules the same. And more importantly, we kept the temperature the same. And so T here is the same as it was in the first case. Right? But all we did was we changed the volume. Now the volume is smaller. And so now, if we think about pressure, temperature is the same, so the energy in the system is the same, but the volume is now smaller, okay? And so, if we have the same energy, but now we have a smaller volume, that means that the pressure in the system must go up, just based on pure math, right? If energy is the same, but now the volume is smaller, if we divide that energy by a smaller volume, that means we're going to get a larger pressure. Okay? And so if V is reduced and temperature and number of molecules stays the same, that means the pressure must increase. And so whenever you're thinking about pressure, one useful way to think about it is as a sort of energy density, right? The energy per unit volume. All right. Another way, but equal way to think about pressure is you could also think about it as a force per unit area. So if you look at the units here, these are equivalent. All right. So I'll ask you to do that on your own time. But thinking about pressure as, a force per unit area, so you could think about it as the force of the gas molecule colliding with the container wall per some area, or the gas molecule colliding with some area of the container wall, right? So thinking about pressure in these terms is going to be useful for when we start doing force balances later on in this course.